Have you ever wondered how your computer can search through millions of files in just a split second? Or how the undo button in your software knows exactly what to do next? Well, the secret isn't magic. It's something called data structures. And I know, that might sound super technical, but they're really just clever ways of organizing information, a problem we all deal with every single day. So, let's start with a little thought experiment. Picture a huge library. You can probably find one specific book out of thousands in just a few minutes, right? Okay, now, picture your bedroom on a really messy day. Trying to find your keys in that chaos can feel like an impossible mission. So what's the difference? It all boils down to one simple word: structure. The library has it, the messy room, not so much. And that, right there, is the entire idea behind a data structure. It's basically the digital version of that organized library system. It's a very deliberate, intentional way of arranging data so that finding it, adding to it, or removing it is as efficient as humanly possible. Think of it as the blueprint for how our entire digital world is organized.
Now, when we keep saying efficient, what are we talking about? We're talking about these key actions right here. Every time you save a file, you're inserting data. Every time you search for a contact or delete an email, you're performing one of these operations. The data structure is what's working behind the scenes to make sure those things happen in a blink, not an eternity.
Okay, so there are a bunch of different blueprints or structures we can use, and each one has its own special strengths. Let's start with one of the simplest, most common ones out there, the stack. Its entire philosophy can be boiled down to 4 little words: last in, first out. You absolutely do not need to be a programmer to understand this one. Just imagine a stack of clean dinner plates at a buffet. When a new plate comes out of the dishwasher, where does it go? Right on top of the stack. And when you go to grab a plate, which one do you take? The one on top. You'd never try to wiggle one out from the middle or the bottom, right? Well, that's a stack.
And that simple act, grabbing a plate, perfectly illustrates the core principle of a stack. We call it LIFO, which stands for last in, first out. The last plate you added to that stack is always going to be the first one that gets taken off. It's simple, it's intuitive, and as you're about to see, it's incredibly useful.
So let's just trace this with some numbers. In programming, when we add an item to the stack, we call it a push. So let's push the number 5 onto our empty stack. Then we push an 8, which goes right on top of the 5. Then we push a 2. So now the very top of our stack is 2. When we want to remove an item, it's called a pop. So if we pop, which number comes off? Of course it's the 2, because it was the last one in.
And here is the beautiful part. This whole structure is unbelievably fast. I mean, think about it. Whether you have 10 plates or 1,000,000 plates in your stack, adding one more to the top or taking one off the top takes the exact same amount of time and effort. You only ever have to touch the top. In computer science, we have a fancy term for this incredible efficiency. We call it constant time, or O of 1. It just means the operation speed isn't affected by how big the collection gets. How cool is that?
You know, you actually use stacks all the time without even realizing it. When you're typing and you hit undo, your computer is popping your last action off a stack of your recent commands. And your web browser's back button, that's just popping the last website you visited off a stack of your browsing history. So the stack is all about last in, first out. But what if you need the opposite? You know, what if you need a system that's fair, with the first one to show up as the first one to get helped? Well, for that, we turn to our next structure, the queue.
And the best analogy for a queue is something we are all very, very familiar with. Just a regular old line at a bank or a grocery store. It's an orderly, fair process that everybody understands without even thinking about it.
The rule here is the exact opposite of the stack. It's FIFO, first in, first out. The first person who gets in line is the first person who gets served. It's the definition of fairness, right? You help whoever has been waiting the longest, not the person who just walked in the door. So in queue speak, adding an item to the back of the line is called an NQ. So first, we NQ the number 5. Then 8 gets in line behind it. Then 2 gets in line behind that. Now, to serve the next item, we DQ from the front of the line. And who's at the front? The 5, of course, because it was the very first one in. Queues are really the silent heroes of orderly processing in our digital lives. When you send 5 documents to the printer, they don't just print in a random order. They form a queue and print one after another. Your computer's processor is juggling dozens of tasks at once by lining them up in a queue. It's all about first come, first served. So, stacks and keys are fantastic for data that exists in a straight line. But what about data that's, well, more complex? Data that has relationships, levels, and branches. You know, like a company's org chart or even your computer's file system.
For that kind of hierarchical data, we need something a little more sophisticated: the tree. A family tree is honestly the perfect mental model for this. You've got generations, parents, children, siblings. It's all about the relationships between them. A simple, straight line just can't capture that kind of complexity. And that is exactly where the tree data structure comes in to save the day.
Now, trees have their own language, but it's really intuitive because it borrows from that family tree idea. The single starting point at the very top is called the root. Any item that has other items branching off below it is a parent, and those items are its children. And finally, an item at the very end of a branch, one with no children of its own, is called a leaf. Take a look at this really simple example. The number 10 is our root. It's the parent of two children, 5 and 20. The simple parent-child link is the fundamental building block for all tree structures, no matter how massive or complicated they get. Okay, now a very common and super important type of tree is the binary tree. The bi in binary means 2, and the rule is just that simple. Each parent can have a maximum of 2 children. We just call them the left child and the right child. This simple rule makes them incredibly powerful and efficient for things like searching.
All right, we have covered a lot of ground. We've gone from messy rooms to stacks of plates, all the way to family trees. So let's just pull it all together for a quick review. If you happen to have an exam coming up, you are definitely going to want to pay attention to these next couple of slides.
This chart is basically your cheat sheet. Look at the key difference here. Stacks and queues are linear. They're defined by how you access them, either last in or first in. And because you only ever deal with the ends, they're wicked fast, O of 1. But the tree is complete.